In section 4.2, which is called the mean value theorem, we're really tying together the two ideas between the average rate of change and the instantaneous rate of change. Just as a reminder, the average rate of change, or AROC, is when you basically connect 2 points and you do the slope of the secant line. So this is just the slope that you've been doing ever since algebra. The instantaneous rate of change is the slope at 1 point, and that's what we call the derivative. So the mean value theorem is going to connect these two types of rates of change. You have to satisfy the hypothesis for this theorem. So the function has to be continuous at every point on a closed interval. So far it's just like the extreme value theorem. Unlike the extreme value theorem, in order for the mean value theorem to hold, the function also has to be differentiable at every point within the interior. As long as those conditions are met, then there is at least 1 point at x equals c within the interval from x equals a to x equals b at which the secant slope equals the tangent slope. So let's see what that means. Let's take a look at this little diagram here. If we have a continuous function over a closed interval, so let's say we're going from x equals a right here to x equals b. If we connect those 2 points with a secant line, you could calculate the slope by doing AROC, f of b minus f of a all over b minus a. Okay, so that's the average rate of change. Now, since the function is continuous over the closed interval from a to b, and it's also differentiable, so a reminder about that. There's no cusps, there's no corners, and there's also no vertical tangents on this particular graph. Then this mean value theorem says that there's at least 1 point at which the tangent slope will equal the secant slope. So as I kind of envision a whole bunch of little tangent lines, and you don't have to draw this part, but you know, if you just draw a couple of tangent lines, those slopes don't quite match yet, but then all of a sudden right about here, that tangent slope at this location matches the secant slope. So the way we talk about slope at 1 point is by f prime, and that location is C. So this is the IROC, and this is the AROC. Okay, so I'm going to go ahead back up to the little mean value theorem box up here, and that's what I would fill in. There's at least 1 point. As long as the function is continuous on a closed interval and differentiable at every point on the interior, then there is at least 1 point at which the derivative will match the slope of the secant line. And that secant line is the line that connects the two endpoints of the interval. It's supposed to be a b minus a. Okay, so that's essentially it. Now you've already seen this. If you remember Rolle's theorem. Rolle's theorem was a select or a specific portion of the mean value theorem. All right, let's take a look at example 1. It says, show that the function f of x equals 3x squared minus 4x plus 14 satisfies the hypotheses of the mean value theorem, and then find each value of c in the interval that satisfies the mean value theorem. Well, first of all, we have a closed interval, so it satisfies that portion. It's continuous because it's a quadratic, so the first part of the hypothesis is satisfied, and then it's differentiable. It's differentiable because if you take the derivative of this guy, f prime of x, you will get 6x minus 4. Okay, that is a function that is it is continuous. There's no domain issues or anything like that, so we know that it's going to be differentiable everywhere within the domain. So we can go ahead and move on to finding the value of c that satisfies. Okay, so this is the value of c. This is just talking about which x value. Okay, so which x value satisfies the mean value theorem? So all you're going to do is set AROC equal to IROC. Well, a rock using -4 and -2 as your endpoints for x, it's just going to be f of -2 minus f of -4, all divided by -2 minus -4. And we're going to set that equal to f prime of x, which we already said was 6x minus 4. Okay, so f of -2, just go ahead and plug it in and simplify. And if you plug in the -2, you're going to get 3 times the -2 squared, so -2 squared is going to be 4, so that's going to be 12. 12 minus a 4 times a -2, so that's going to be 8, so 12 plus 8 is 20, 20 plus 14 is 34. Again, that just comes from the original function as the notation shows. And then go ahead and plug in the f of -4. Okay, so my 2 looks a little funny. There we go. And then we're still setting that equal to the 6x minus 4. And we're going to bring that over to here. And so we're going to have -44 over 2 equals 6x minus 4. -22 equals 6x minus 4. -18 equals 6x. So we're getting an x value of -3. Now, it won't always happen that the value that you get falls within the interval. And it also won't always be true that the x value falls exactly in the middle of the interval. That just happened to be true for this case because it was a quadratic function. So this is saying that if you were to graph f of x and you were to connect the 2 points from x equals -4 to x equals -2, that slope would be the identical slope as the tangent line at x equals -3. So that's the mean value theorem, just connecting the two of them. All right, for example 2, we're given a function f of x equals the absolute value of x minus 1. And this problem is asking us to show that this function does not satisfy the hypotheses of the mean value theorem on the interval from a to b, where a equals 0 and b equals 3. So I'm going to have you press pause on the video right now, and please do this problem to completion, and then check your answer when you're done and come on back. Did you do it? If you didn't do it, press pause. Come on. Okay. Okay, as you can see from my graph, I've shown you the function f of x equals the absolute value of x minus 1. This function, although continuous on the closed interval, is not differentiable at x equals 1, where there is a corner, and corners are not differentiable because the slope from the left does not equal the slope from the right. And again, reminding you that a derivative is a limit, and the limit has to be the same from the left and the right in order to exist. So because this does not satisfy the hypotheses of the mean value theorem, we're going to go ahead and graph together the line through the points a comma f of a. So if you plug in 0 into the function, you're going to get a y value of 1. And then at b equals 3, you're going to get a value of 2. So if you connect those guys, okay, f of 0 we just said was 1, f of 3 was 2. So if we try to do the mean value theorem, and we do f of 3 minus f of 0 all over 3 minus 0, we're going to get 2 minus 1 all over 3. So we're getting a 1/3. Okay? And the function itself, f prime of x, is going to equal 1 for x greater than 1, and the derivative equals a -1 for x less than 1. There are no other values of the derivative of this function. And again, there is no value that satisfies the mean value theorem because the hypotheses didn't hold. okay? So there's no value of c. The physical interpretation of the mean value theorem, basically, if your car's average velocity from t equals 0 to t equals 5 is 20 miles an hour, at some point in that interval, then your instantaneous velocity, meaning the speed at any one point, so on your speedometer, had to have read 20 miles per hour. And this is where they can get you with speeding tickets if you go through toll booths. They can calculate how far you've gone and the time that it took you based on when you go through the toll booth. And if your average velocity is higher than the speed limit, that means that you were speeding at some point. So that's calculus in the real world for you. Let's go ahead and take a look at example number 3, and this is we're revisiting increasing and decreasing functions. So I would like you to do this problem on your own, and I'm going to put up the solution. You can check your answer, and that will be the end of this section. Okay, I'm about to put up the solution. Did you do it? If not, press pause now. Okay, let's see how you did. The first thing is realizing that the original function has a domain of everything, all values of x. So you can go ahead and take the derivative right away. Set the derivative equal to 0 to find critical points. And we're getting 2 critical points out, plus or minus 2 over radical 3 for the x value. The derivative function itself will never fail to exist, so we're not getting critical points out that way. And then I went ahead and set up my number line over here. These are the 2 critical points, negative 2 over red 3 and positive 2 over red 3. At each of those, the derivative had a value of 0. So then I just tested regions. I got a positive, a negative, and a positive. And that tells you what your function is doing, increasing, decreasing, increasing. So again, here's the justification that your AP graders would need to see. They don't look at your number chart. The number chart is for your information only. So this is the justification. You know that a function is increasing where its derivative is positive, and you know it's decreasing where the derivative is negative. And that is all, my friends. Talk to you next time. Bye. Well, actually, I won't talk to you next. I'll talk to you, but you won't talk to me. Okay, you know what I mean. Bye.